This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
We are frequently told the energy transition requires building massive new power plants. But look at the grid we already operate. The global civil infrastructure network is bleeding kinetic energy. Consider municipal water mains. Every day, millions of gallons are pumped through these networks. To prevent pipe bursts at your faucet, heavy industrial valves artificially drop the water pressure. That pressure drop is uncaptured mechanical energy. The same mechanical waste happens in wastewater treatment. These massive facilities run continuous, unoptimized aeration cycles 24 hours a day, burning electricity to keep fluid in motion without recovering any of that momentum. District heating networks operate on similar inefficiencies. Main circulation pumps force hot water across entire cities, yet their mechanical loads remain untracked and unoptimized. Municipal utilities treat these systems as static energy consumers, but the physics dictate otherwise. These networks are active kinetic reserves. Rather than constructing a new utility from scratch, we can deploy an energy recovery infrastructure layer, a physical network that intercepts rotating machinery and captures the wasted mechanical force directly at the source. The next phase of public infrastructure relies on capturing this invisible waste. It converts constant operating liabilities directly into generating assets. Energy recovery follows a strict equation: power equals torque times angular velocity. To capture this, rotational force is channeled into a radial flux permanent magnet generator. Inside, spinning neodymium magnets convert torque into raw alternating current. But you cannot feed raw, unregulated alternating current back into an industrial facility. This strict power electronic stack conditions the energy. Raw AC exits the generator, enters a rectifier, and feeds a central DC bus. From there, it passes through a silicon carbide inverter, minimizing thermal losses and maintaining system efficiency above 95%. Proving these physics in an isolated environment is straightforward. Deploying the technology across a global grid requires mass production. Bespoke, custom-built generators cannot meet that scale. Hardware must be standardized. This 25 kilowatt flux block is the interchangeable baseline unit. Every deployment follows a rigid rule: total power equals 25 times N. These modules stack, scaling from a 20 kilowatt micronode to a 2 megawatt industrial array. Using a single standardized block eliminates custom engineering on site. It collapses inventory complexity and removes friction from the supply chain. By locking the physics of energy conversion into plug-and-play modules, the recovery infrastructure transitions into scalable industrial hardware. This modular framework is currently deployed in Sofia, Bulgaria. The city serves as phase 1 of a national program, acting as the primary proving ground for civil infrastructure integration. The initial deployment installs FD water nodes directly into the municipal water mains. This visual demonstrates the fluid dynamics of an inline turbine. As standard pressure drops of 1 to 5 bar pass through the system, the node captures the kinetic flow. Each integrated cluster is engineered to generate 100 to 500 kilowatts of continuous power. The second deployment site is the Kubratovo Wastewater Treatment Plant. By retrofitting the aeration blowers and sludge pumps with variable frequency drives and advanced controls, the facility's overall energy consumption drops by 25%. The third site connects to Toplofikacia Sofia, the local district heating authority. Upgrading the main circulation pumps and local substations reduces the network's electrical load by 10 to 20%. For any municipal operator, the primary barrier to these upgrades is facility downtime. Shutting off a city's water supply to install a generator is not an option. Because the hardware arrives on standardized, pre-assembled skids, mechanical mounting and electrical integration are highly predictable. Installation requires under 48 hours of facility downtime. You do not need to halt a living city to upgrade its infrastructure. You simply plug into the existing flow. Yet, physical hardware alone cannot adapt to the daily, fluctuating demands of a massive urban grid. To maintain stability, the network is managed by a central intelligence layer, the Data Monitoring and Intelligence System. The edge controller continuously ingests high-frequency telemetry, RPM, voltage, current, and vibration at 10 kHz. The software runs an algorithmic loop, dynamically adjusting load profiles and thermal constraints to satisfy a single mathematical objective: maximize net energy output minus system losses. The software layer transforms passive metal components into an intelligent, self-optimizing grid asset. The rollout strategy relies on strict validation. Expansion beyond the city limits is locked until the Sofia pilots mathematically prove a clean 5-year capital payback. Once that financial threshold is crossed, it acts as a scale trigger. As shown here, Phase 1 validation unlocks Phase 2, immediately replicating the standardized water nodes across regional utilities nationwide. The network then enters Phase 3, expanding out of municipal utilities and into the high-torque, continuous environments of heavy industry. Facilities like large-scale open-pit mining operations become prime targets for extreme mechanical energy recovery. Metallurgy and cement manufacturing follow closely. These are punishing thermal and mechanical environments that require robust, standardized motor optimization to survive. Finally, the rollout reaches Phase 4, establishing a fully integrated, countrywide energy recovery grid. This scaling trajectory is strictly deterministic. It is unlocked exclusively by verified thermodynamic output and hard financial returns. Even with proven physics, a bottleneck remains. Municipalities rarely have the budget to carry massive upfront capital expenditures for infrastructure upgrades. This chart illustrates how to bypass local debt limits. Instead of relying on municipal budgets, the installations are backed by a multi-source deployment fund. Capital is drawn from specific high-tier institutional streams, namely European Union cohesion funds and Green Deal grants. This is reinforced by targeted debt financing deployed by institutions like the European Investment Bank. The cycle runs on an energy-as-a-service model. The capital injection funds the upfront installation. The system captures wasted energy, and the financial savings strictly pay down the initial cost. The math is rigid. A €1 million installation generates €200,000 in annual savings. That locks in a highly predictable 5-year payback mechanism. FluxDrive is a verifiable engineered asset class. It absorbs institutional capital and utilizes basic physics to generate predictable, scalable infrastructure yields.